So let me start. It's my pleasure to introduce our next invited speaker, Mirjam Dürr. Mirjam Dürr was born in Vienna, Austria, where she received a degree in mathematics from the University of Vienna in 1996. She received a PhD in applied mathematics from University of Trier in 1999. And after that, she worked as an assistant professor at Vienna University of Economics and Business Administration, as a junior professor at Technical University of Darmstadt, as an university docent at the University of Groningen, the Netherlands, and as a professor of nonlinear optimization in Trier. Since October 2017, she is a professor of mathematical optimization in Augsburg. Professor Dürr is a member of the editorial boards of the journals Mathematical Methods of Operation Research, Journal of Global Optimization, Optimization Methods and Software. And in addition, she is member of the editorial of book series Springer Briefs in Optimization. In 2010, she was awarded a VC grant by the Dutch Organization for Scientific Research. And in 2012, a research grant by the German-Israeli Foundation of Scientific Research and Development. She is a former principal investigator and now member of the Scientific Advisory Board in the Research Training Group, Algorithmic Optimization at the University of Trier. And well, the title of her talk today is Tackling Discrete Optimization Problems by Continuous Methods. When you want.
Thank you very much. Let me share my screen. Does this work? Can you just give me small feedback whether this?
Yeah, it's perfect.
Okay. Perfect. Thank you very much. So, well, thank you very much for this kind introduction of myself. I'm happy to talk to you today about my research field, and I've chosen the title Tackling Discrete Optimization Problems by Continuous Methods because it describes, well, kind of the focus of my research, which is to merge the discrete world and the continuous world. So I have prepared a talk where I'm going to take you on a tour through different aspects of my work. And I'm going to start by describing a certain combinatorial problem, which is going to be the main example which I use to illustrate things throughout this talk, which is the stable set problem. So I'm going to explain what that is and how it works. I'm going to talk a little bit about the P versus NP problem. So the polynomial versus non-polynomial complexity classes. Then I'm going to talk about the difference between local and global optimization because this is going to play a role. Next, I'm going to introduce a concept which is called copositivity of matrices, and I'm going to explain what that is and how it relates to the things that we're looking at here. And I'm going to conclude by talking about the kissing number, which then again connects to the stable set problem, which we started with. So let us start and let us discuss the stable set problem. And as an applied mathematician, I would like to introduce this problem by looking at a practical application. So let's assume we are engineers and we are given a certain number of antennas, as you can see them here. And our task is to assign frequencies to these antennas. So each of these antennas should be assigned a frequency, and we are allowed to assign the same frequency to different antennas, but we should make sure that there are no interferences. So interferences between antennas, they disturb the flow of information, so we would like to avoid that. And now you can see that there are these lines between the antennas which depict whether there could be an interference between the two. So for example, between these two antennas, we should be careful because there is interference. Whereas, for example, between this one and that one, there will be no problem. There will be no interference at all. So how can we assign antennas? Well, we can assign, for example, to these 4 antennas the same frequency, and this will make sure that there is no interference between these 4, because the interferences, they are shown by these arcs between or by these lines between the antennas. So this would be an option to assign these 4 the same frequency. Another option would be to take these 6 and assign to them the same frequency. And of course, the rest of the antennas then should be assigned different frequencies. And this is an application that appears in real world settings. And now we would like to look at the mathematical setting and the mathematical model, how we can tackle this by the tools of mathematics that we have. So the tools that we use here, the main tool is graph theory. So we get rid of the antennas and we just look at a graph, where you can see a graph depicted here on the right-hand side. What is a graph? Well, a graph consists of 2 objects, a set of vertices, which I denote by V, and a set of edges, which are connections between the vertices. And in this picture, the vertices are these dots here, and the edges are the connections between the dots. And you can see that this graph here represents the antenna setting that we had before. So this is a graph. And now what has this got to do with the frequency assignment problem? Well, what we're looking for is a so-called stable set in this graph. So a stable set is a subset of the vertices of the graph, such that there are no edges between the vertices in this subset S. So if you look in the picture, if you look at the red vertices here, you can see that these red vertices form a stable set in the sense of this definition, because if you pick any 2 vertices in this set of red vertices, then, well, there is no edge which connects any pair of vertices in S. So this is a stable set. And what we're now looking for is the so-called stability number, which is denoted by alpha of G. And the stability number is the cardinality of the largest stable set in this graph. And in this example that I have drawn here, it is not hard to verify that the largest stable set in this graph is exactly this set of red vertices, which I have drawn here. And this means that the stability number is 6. So alpha in this graph is 6, because the largest stable set in this graph consists of 6 vertices. So this is the problem that I'm going to use throughout this talk to find in a given graph the cardinality of the largest stable set in this graph. You can formulate a decision version of this stable set problem. And the stable set problem in the decision version says, well, given a graph G and a number K, which is an integer number, the question is, decide whether this graph has a stable set of cardinality K, yes or no. So this is the decision problem. And it is well known that this is, from the complexity point of view, a very difficult decision problem. So it was shown by Karp that it is an NP complete problem. And this leads me to a very short discussion about the complexity classes P and NP. So this is my second point in this talk. Let's look at the definition. So we have complexity classes P and NP. And the complexity class P consists of all decision problems that can be solved by a polynomial algorithm, which basically means an algorithm whose runtime is somehow bounded by a polynomial in the input parameters, or by the coding length of these input parameters. And the complexity class NP consists of all decision problems where it can be decided by a polynomial algorithm whether a given solution that somebody gives you, whether this solution is correct or not. So let's look at our example of the stable set. Let's look at this graph again here. So we're given a graph G and a number K, and let's take K equals 6. And then assume somebody gives you a set S, the set of these red vertices, and this somebody claims that this is a solution. The question is, can you verify in polynomial time whether this is a solution? So the question is this set S, is it indeed a stable set, and is it of size 6? And both questions can be answered in polynomial time very easily, and the answer is yes. And hence we see that this problem, the stable set problem, is a problem which is in this complexity class NP. So if somebody gives you a solution, then it is easy to verify that this is indeed a solution. The other question is, how do I find such a set S? This is an entirely different question. So the situation is that no polynomial algorithm is known, which will give you a stable set of this size. And the consequence is, since we don't have a polynomial algorithm, that the problem is not in this problem class P. Or at least I should say, unless P equal NP. So it is actually an open question, as you probably all know, to decide or to answer the question whether these two complexity classes are actually the same. This is still not solved. And these complexity classes were, or actually this question was already defined in a letter by Kurt Gödel to John von Neumann, which he wrote in 1956, and where he kind of phrased this problem, whether P equal to NP, and he posed this question. And he wrote in this letter about a function psi of n, which is somehow the runtime that an algorithm needs on a machine. And the question is how fast this function psi of n grows for an optimal machine. And if there really were a machine such that this psi function is roughly linear or even roughly a quadratic function, then this would have consequences of the greatest importance, Gödel writes. Namely, it would obviously mean that the mental work of a mathematician concerning yes or no questions could be completely replaced by a machine. So I found this interesting to see that already, what is it, more than 60 years ago, 65 years ago, actually, this question was already raised, and it is still an open question. You probably know that it is one of the Millennium Problems by this Clay Institute. And if you solve, or if you answer this question, whether P equals to NP, you will get a lot of money. And one way to show that P equals NP actually is to come up with a polynomial algorithm for this stable set problem that I described. So I should add that at the moment, most researchers believe that P is not equal to NP, but still it is not known. And I have drawn here a picture for you of an exponential function and a linear and a quadratic function, just to remind you of the importance of well, exponential growth. As we all know, this is something which is not desirable. Okay, so this concludes my little detour to the P equal NP question. And I would like to go on to talk about the stable set problem, which is, of course, a discrete optimization problem, a combinatorial problem. And I'm going to discuss next how this discrete problem can be treated with continuous optimization methods. So first of all, we should, before we begin, we should talk about how we can encode graphs such that a computer or an algorithm can use them. And I have drawn a little graph again here for you. because maybe you are not that familiar with graph theory. So we need to somehow define what is the vertex set and how we deal with the edges. And usually the vertex set of a graph is just defined as, well, the numbers from 1 to n. So basically you name each vertex by a number from 1 to n. So in this case, we have vertices from 1 to 6, and I have written the numbers here to make things more easy. So the vertex set is easy. And what do we do with the edges? Well, the edges we can code in the so-called adjacency matrix, which can be seen here. So for a graph with n vertices, we have an n by n matrix, which is the so-called adjacency matrix. So in our case, we have a 6 by 6 matrix because we have 6 vertices. We put zeros on the diagonal of this matrix, and we put ones or zeros in as the entries of the matrix, depending on whether there is an edge in position ij. So there will be a 1 in position ij if and only if there is an edge between the vertices I and j. So for example, there is an edge between the vertices 1 and 2. So in position 1, 2 of this matrix, there should be a number 1. And also because it's symmetric, in the position 2, 1 of this matrix, there should be a 1. On the other hand, there is no edge between vertices 1 and 3. So in position 1, 3, there is a 0, and similarly in position 3, 1, there is a 0. So this is how the adjacency matrix encodes the structure of the graph and gives the pattern of where there are edges and where there are no edges. Okay, and this matrix can now be used to, well, to come up with different formulations for the stability number problem. So I will denote the adjacency matrix of a graph by capital A. And I need to define a set, which is the standard simplex. So it's the set of all x in Rn, such that x is non-negative and E transpose x is equal to 1, where E is the vector of all ones. So basically this constraint E transpose x equal to 1 means that the sum of all the entries xi should be equal to 1. So I've drawn a little picture here of the simplex in R3. This is it's sometimes called the standard simplex, or sometimes it's called the unit simplex or the probability simplex. I'm sure you are familiar with this object, and I'm going to denote it by delta. Well, this is the definition. And now we can use this matrix A, the adjacency matrix, and this standard simplex delta to consider an optimization problem. And I will, so this is the optimization problem. We want to minimize a quadratic function, which is the quadratic function which comes from the matrix A plus I. So A was this adjacency matrix of the graph, and I is the identity matrix. And well, so this gives a quadratic form, if you like. And we would like to minimize this quadratic form over this simplex. And we will denote by m of g the optimal value of this problem. So this is an optimization problem that you can write down. And why is it interesting? Well, it is interesting because of a theorem which is also rather old and which was proved by Motzkin and Strauss in 1965, and which says that the stability number alpha of g that we have been talking about is exactly equal to the reciprocal value of this optimal value m of g that I defined up here. So this is a quite remarkable result that Motzkin and Strauss proved. And interestingly, the proof is quite easy. It's a proof by induction on the number of vertices of the graph. And I really recommend reading this paper. It's a pleasure to read this, and it's a quite surprising result. So what does this give us? Well, it gives us that we can compute this graph parameter, which is somehow, if you want, the solution of a combinatorial optimization problem. We can get this as the solution of a continuous optimization problem, this one, M of G. So this is a first connection between the discrete world and the continuous world. And well, so this is interesting because now we can start using methods from continuous optimization to solve, well, this combinatorial problem of computing this graph parameter alpha. Okay, so I'm going to take this to the next slide, that alpha of G equals 1 over this minimum, and I'm going to write it in this form: 1 over alpha of G equals the minimum of this optimization problem that we discussed. And now we can see a drawback. The drawback that turns out to be, well, a nuisance or very unfortunate. The drawback is that this quadratic function that is our objective function of the minimization problem, this is not, unfortunately, a convex function. So this is a quadratic function, but it's not convex. So it roughly looks like this picture. There are directions where the function is convex, like here, but there are other directions where the function is concave. So this is just a property that can be seen very easily, that this is not a convex function. And the problem is this connection between the stability number and the solution of this continuous optimization problem. This connection is only true if we really look here at the global minimum of this quadratic optimization problem. So we do need the global minimum. We are not satisfied with the local minimum. And well, computing the global minimum of a non-convex function is usually not so easy. So as I said, local minima are usually easier to compute than global minima, because you can just start somewhere and, well, roughly speaking, go downwards till you reach a local minimum. So this is quite easy, but what we're interested in is the global minimum. And global optimization, I always preach this to my colleagues: global optimization needs global information. You cannot solve a global optimization problem by just looking at your function locally. You need information about the function on the entire domain that you're searching. So what can we do? Well, global information, how would it look? So for example, convexity would be a global property. If you know that a function is convex, then this is a global property, which can be described by a picture like this. And in this case, it is well known that any local minimum of such a convex optimization problem is already a global minimum. Unfortunately, in our setting, we have a non-convex function, as I showed you. And for non-convex functions, this is also a well-known property. There can be local minima that are not global minima. So what can we do? We have now reformulated the stability number as the solution of a quadratic optimization problem, which is a continuous function, but with a non-convex function. So what do we do? And here there comes this concept of copositivity, which I announced that I was going to talk about. And I would like to explain next how this helps to solve these kind of problems. So this was our result, which came from this theorem of Motzkin and Strauss. The 1 over the stability number equals this minimum of this quadratic function over the standard simplex. And now I will introduce a technique which is called lifting. And it basically means that instead of working in the space Rn, where this variable x lives, I'm going to a higher dimensional space, and I'm going to explain how this works. So we're looking at the objective function of this minimization problem. The objective function is this quadratic function X transpose times the matrix A plus the identity matrix times X. And now we're going to rewrite this function. So obviously the result of this function is a real number, right? So I can interpret this as a 1-by-1 matrix and write that this equals the trace of this 1-by-1 matrix. This is obviously the same thing. And now I can use properties of the trace that we teach our students in the first semester, which is that the trace is invariant with respect to cyclic permutations. So I can take this, term X transpose and move it in a cyclic way to the end of this expression, which gives that this equals the same as the trace of the product of two things, the adjacency matrix A plus identity times this X transpose, which is of course a rank 1 matrix that we have here. So this just comes from properties of the trace. And now if we remind ourselves of the definition of the so-called Frobenius product of matrices, then we see that the trace of the product of these two matrices is precisely the inner product of these two matrices. So I have recalled here for you the definition of the Frobenius inner product of two matrices. It's just for symmetric matrices, it's the trace of the product of the matrices. And you can work it out that this is the sum of all the pairwise products of the entries. Okay, so we have rewritten this objective function of our optimization problem. We have rewritten this in a certain way, which is obviously true. But why do we do this? Well, now we introduce a transformation of variables, if you wish. So we define a new variable, capital X, which is going to be a matrix variable. And we define it to be this rank 1 matrix XX transpose, which appears here. And if we do this, then the quadratic term that we started with, which was a quadratic term in this variable X from Rn, in this vector variable, this quadratic thing becomes a linear term in the matrix variable. So this is nice because we move from quadratic terms to linear terms. And of course, linear terms are always easier to work with because, well, if you minimize a linear function, then it is obviously a convex function and every local minimum is a global minimum and so on. So things are much easier. And we can use this in an optimization problem, which I will discuss next. This is the so-called standard quadratic optimization problem, which is a bit more general than what we had. But this problem, which came from Motzkin-Strauss, was of this type. Just the matrix Q was of a particular form, including the adjacency matrix and the identity matrix. So let's look at this problem where we minimize a quadratic form over the standard simplex again. And it is known that if this matrix is indefinite, then this is NP-hard, which means there is no polynomial algorithm known to solve this problem, in spite of the very easy structure. But still, this is a very hard optimization problem already, even if there's only one negative eigenvalue. Okay, so let's introduce this lifting approach and use it for our problem. Then we can see that this quadratic form becomes a linear term in the new matrix variable capital X. We remind ourselves that the capital X was this rank 1 matrix, XX transpose. And we should keep in mind that the vector X that we started with, it came from, or it was supposed to be non-negative entry-wise. And we can also take this constraint and lift the constraint, if you wish, so we can square the constraint. And then we get a linear constraint in the matrix variable, and there appears a matrix capital E, which is the all ones matrix, which is the all ones vector multiplied by itself. So it's quite easy to see that these two are equivalent because we just use this lifting technique that I discussed. But if you look at these problems, then from a numerical point of view, these constraints, or this constraint actually that the capital X matrix should be a rank 1 matrix, this is a numerically very hard and a non-convex constraint actually. So the non-convexity has to move somewhere, or at least the complexity that this is not a polynomial problem, this should move somewhere. Okay, so what can we do next? We can now kind of convexify the problem. So let's introduce a definition. We introduce a set, which turns out to be a cone of matrices, which are called completely positive matrices. And here is the definition. So it's the convex hull of all the rank 1 matrices XX transpose, which come from a vector X, which is entry-wise non-negative. So these are precisely the matrices that appeared here. And now we just take the convex hull of all of these matrices. And it turns out that this is a matrix cone. And by definition, it's a convex cone because it's the convex hull of some set. So it's convex. Well, what you can do next is you can show that this standard quadratic optimization problem that we started with, that it is equivalent to the following linear optimization problem over this cone of completely positive matrices. So we have this minimization problem where we minimize the linear function q times x, which is the same as we had here. Subject to the constraint that, well, there is a linear constraint, the inner product of the all ones matrix and x should be equal to 1. This comes from up there. And now we replace actually these constraints by the constraint that the matrix variable that we're dealing with should be in this cone of completely positive matrices. So it's not hard to show the equivalence, and equivalence means that these two problems, the standard quadratic problem and this conic problem, they have the same optimal value. And if we have an optimal solution of one problem, we can reconstruct optimal solutions of the other problem. Let's put it like this. Okay, so now we have to deal with this cone and let's look about this cone. And I forgot to mention, the interesting thing that we have here is that we have now shown that this non-convex standard quadratic optimization problem is equivalent to this problem, which is a convex problem, of course, because it has a linear objective, it has a linear constraint, and there is a cone constraint, which says the variable should be in a convex cone. So this is a convex optimization problem. There are no local minima, and the only minimum of, or the only minima of this problem are the local minima, which are already global, and they give us also the global minima of this standard quadratic problem. So this is nice, but there must be a drawback somewhere. So I have written here the definition of this cone of completely positive matrices again. You can write it in an equivalent form as the set of matrices which have a symmetric factorization of this form BB transpose with a non-negative matrix B. So this is this cone that we introduced. And there is a dual cone which appears in the dual optimization problem. And this is the so-called cone of copositive matrices. And here's the definition. Those is the set of matrices which are symmetric and which have the property that this quadratic form induced by the matrix is non-negative for all the x that are non-negative. So x in Rn plus means x is a vector which is component-wise non-negative. All the entries of x are non-negative. And I have drawn here a picture for you of the copositive cone of 2 by 2 matrices, symmetric 2 by 2 matrices. So we only have 3 entries. We have the one diagonal entry, the other diagonal entry, and the off diagonal entry. And maybe you can see this if you look at this, how do you say this? sphere here. Everything which is above this lines corresponds to a matrix which is copositive, a 2x2 copositive matrix. The bad news is that these cones are hard to deal with. So testing whether a matrix is in one of these cones is a question which is not polynomial unless P equals NP. So the complexity now goes to the cone. But still, what we have seen is that the stability number of a graph with n vertices and adjacency matrix A can be written as either a primal or a dual problem over one of these two cones. So this would be the problem that we have seen. And this one is the problem that is the dual problem to the other one. So both have the same objective value one can try and compute the stability number via these optimization problems. The consequences of this result is that not every convex optimization problem is easy. So there are optimization problems which are convex, for example, these two, which are not polynomially solvable. But this approach opens new ways of approximating these two cones, and by this getting approximations for the stability number also. I should say that this result on the stability number has then been extended to more general quadratic optimization problems by Burer in 2009 and other authors later, and also to a number of other combinatorial problems. So not only the stability number problem. Okay, I would like to conclude my talk in the last few minutes that I have by talking about the kissing number. So what is the kissing number problems? And you can look at this number in different dimensions. So let's look at it in dimension 2. So in dimension 2, the question is how many unit disks can be arranged around one central unit disks without overlap. So imagine taking a few coins of the same size and trying to arrange them around a central coin, and then you will see that this is an arrangement that cannot be improved. So this means in R2, you can take one central ball and you can arrange 6 of these balls or disks around the central one. So the kissing number, because this is called kissing, if you arrange them like this, the kissing number in dimension 2 equals to 6. Now let's look at dimension 3, and then we work not with disks, but with balls. So you can think of these Austrian sweets that you maybe know. And the question is, how many of them can you arrange around a central one without overlap? And if you play with this a little bit, then you can see a configuration which involves 12 spheres around one central sphere. And the question is this optimal, or can you maybe do 13? And this was a famous dispute in the year 1694, where Newton claimed that, well, 12 is the optimal number in dimension 3. And this person, Mr. Gregory, claimed that it's possible to do with 13. And you can take a guess who was right. So Newton was right, but it was proved only many years later in 1953. So how can we do this as a general, or deal with this as a general problem? We would like to, well, study dimension D. So tau D is the kissing number in RD. It's the maximum number of unit balls which can be arranged around a central ball without overlap. And well, I just give you a few numbers of what is known. So for most dimensions, it's not known, and only some interval bounds are known. So how can we model this? And I claim that the kissing number can be modeled as the stability number of an infinite graph. So what is an infinite graph? An infinite graph is a graph with a vertex set that is, well, not finite. So we have a vertex set V, which we are going to view as a compact metric space. And for example, you can take this unit sphere, which I have drawn here. So I mean here the sphere and not the ball. In RD, it's the sphere SD-1. So this is our vertex set. The edge set is, of course, some subset of V times V. And in our example, we're going to use the definition that two points are connected by an edge if the angle between them is between 0 and 60 degrees, excluding the boundaries of this interval. So if we look at this vertex here, the other vertices connected by an edge to this vertex are the green ones, excluding this one and excluding this one. And well, now you can define a stable set just as we had it before, and the stability number alpha is the cardinality of the largest stable set in a graph. And in this case, if we define the graph as we did, we get alpha equal to 6. And it's not hard to see that precisely this graph that I took as an example, this infinite graph, models the kissing number. And you can recover here the kissing number in R2. And this holds in general dimension. And well, so we had seen that the stability number can be written as a linear conic optimization problem of one of these cones of completely positive or co-positive matrices. And what we did in a paper is to generalize this for infinite graphs, which means that we needed to generalize matrices somehow to some infinite dimensional setting. And what we did is we used continuous Hilbert-Schmidt kernels. So the set of these kernels is just, well, the set of functions basically of from V times V to R, which are symmetric and continuous, symmetric in the usual sense. And then you can, similar to Bochner's approach for semi-definite kernels, or positive kernels, I think he called them, you can introduce co-positive kernels, which is a generalization of co-positive matrices, where we call a kernel a co-positive kernel if for all continuous functions which are non-negative, we have that this integral is non-negative. And the set of all these co-positive kernels be denoted by cop V. And then what we did next is we looked at the dual set of this set of co-positive kernels, which is a subset, of course, of the dual space, which means we need to move to the space of Borel measures on V times V. And by definition of the dual cone is defined as the set of all these measures, such that the duality pairing between the kernel and the measure is non-negative for all kernels which are copositive. And this duality pairing is just integrating K with respect to mu. Okay, so this is the definition basically, but it's not good for optimization purposes. For optimization purposes, we need the extreme rays or the generating rays of that cone. And we were able to characterize the generating rays of that cone. And it turns out these are product measures of the form mu times mu, where mu is a non-negative measure on V. And with this, we were able to come up with a generalization of the stability number formulation for the stability number of an infinite graph. And here it is, and it has a dual problem, which is as before, a maximization problem over this set of completely positive measures. By using these formulations that we have here, we see that we have formulated this graph parameter alpha of these infinite graphs, again, as the solution of a continuous optimization problem, primal or dual. And now we can, of course, use approximation techniques to approximate the cones and get some better bounds, hopefully, for this kissing number or for this stability number. Okay, so this brings me to the end of my talk. I thank you very much for your attention, and I apologize that I was a few minutes too long in talking. Thank you very much.
Thank you very much for your nice talk, Mirjam. And maybe now it's time for some questions. I don't know if somebody wants to ask something. Yes, Volker Merman has raised the hand. Please, Volker.
Thank you very much for the very nice talk.
Thank you.
And thanks for the nice link between continuous and discrete. So you, in particular in the last part, when you made it infinite dimensional, at some stage you will have to go back and go finite dimensional if you want to compute. The approximation that you will have to do then, does that lead again to an alpha of G problem, or do you discretize in a different way the infinite dimensional problem?
I'm not sure I understand your question. So it is true that we have to discretize. Let me maybe go to this slide again, where we have, where we have these two formulations. Of course, it is necessary to discretize these problems, yes, if you want to compute it in some way. But
can you then interpret that discretized, the alpha of G that you get from the discretized problem as a as a finite dimensional problem?
I think we don't get a problem which is of this structure that we had before. This is what you mean?
Yeah.
No, because this would mean that we just discretize the infinite graph in a sense that we throw away most of the vertices and we obtain a finite graph. So this is not how it's usually done. So what you would do is you would try and approximate this. So the approximate, let's look at the structure of this problem again, or of both of these problems, but maybe this one is easier. So this is again a linear optimization problem. We have a linear objective function. We have some constraints. We have a lot of constraints. Actually, here is an infinite number of constraints, but they are linear constraints. These are linear constraints as well. So the thing that you would need to approximate in a sense is this cone. And of course you would need to get rid of the infinitely many constraints and move to some finite setting in some sense. But it will not lead you to problems that you can interpret as a stability number problem of a finite graph. This would be, I mean, you can probably come up with such approximation schemes, but I don't think it would give very good bounds.